I believe we can start. We have already waited a couple of minutes for those arriving late. And thanks very much for being here today in this talk. I guess the micro is working for those on remote. I would like to first of all thank Marco Civera, okay, for being here today. He's coming from Polytechnic of Torino, right, where he did a bachelor, master, and PhD, and now he's a tenure track assistant professor. He works on structural health monitoring techniques, and he's going to be talking about it today. So you will hear. Well, he has a lot of publications. You can go and check the description of the talk. Quite impactful, most of them. And he's also teaching courses on dynamic identification of structures, dynamics of structures, so quite into structures, right? Aerospace structures, I would say. And now, floor is yours, okay? Marco, thanks very much.
Thank you a lot So thanks a lot for the introduction, and also thank you all for having me here. It's nice to be here. So since it's quite an hour for presentation, it's lunchtime, I'll try to do my best to keep it short. So what I will be presenting today is specifically an algorithm for system identification that we basically applied to mechanical vibrations, and especially with Dr. Gabriele De Sena, who invited me here today. I worked a lot on the applications of this algorithm. And this is called the fast and relaxed vector fitting, and I will go a bit into its details. But before that, since this is quite a very niche topic on dynamics of structures, I just wanted to very briefly give you a rough idea of what's the problem at hand. No, so if we are talking about structural dynamics, of course, especially for aeronautics applications, you can have a lot of reasons ranging from control to flight mechanics and everything. But for us, the main point is vibration-based structural health monitoring. So basically, point is if we have damage, how can we detect it? So if we have damage, the idea is that we have a localized reduction on stiffness, and this reduction on stiffness propagates to the dynamic vibration, so the vibrational behaviors of our structure. And this can be interpreted from the natural frequencies, as you see, or the mode shapes, or other derived quantities. So this is structural health monitoring in its dynamical framework. What we will do instead here is talking about system identification, which we can say is the step before that, which means, okay, given a time series of accelerations, how can we extract the model parameters? No? So as you see, a typical example in aeronautical application is ground vibration testing, no, or GVT. So how mathematically we do this is with curve fitting. No, so curve fitting is, as you can imagine, very simple. You have your recorded time series, you convert them in the frequency domain, so easy Fourier transform, and then you need to fit your analytical formulation to those experimental data points, no? Such that you can have an analytical formulation as a function of omega, zeta, and phi, so the model parameters, that can be estimated. So now, since I understand that there is many different backgrounds here, I just wanted to give you, I mean, these are very obvious things, but just to recall, when we talk about model parameters, we talk about natural frequencies in radians per second, damping ratios, and if we are talking on multiple degree of freedoms, of course, we will have multiple natural frequencies, multiple damping ratios, and the mode shapes, no, so the vibrational modes of the structures. Again, for our intent, these are all damage-related quantities. No? So if there is damage, there is a change of stiffness, and if there is a change of stiffness, these parameters should change. What we will also see is that generally in our field, you don't do directly an estimate of omega, zeta, or phi, but you generally you generally obtain these quantities that are called the pole of the systems. Again, I'm sorry if I am telling most of you something that it's very basic stuff. But so basically what you do is that from the poles and the residues of the system, you can see here for a single degree of freedom or for a multi-degree of freedom system, you can obtain the other modal quantities. So how do we define the problem? So of course the point is that there are many different algorithms to do dynamic identification or system identification. These are synonyms. Also because at the end these are transfer functions. No? So as you can see, this is a single degree of freedom example. You can define a transfer function in a number of ways. No? And most of all of them are mathematically equivalent, so there is no point in using one or the other formulation. The key point is about the mathematical convenience of using one or the other formulation to do this curve fitting we were talking about. No? So just to give you an idea, these are for receptance FRF. FRF means frequency response functions, so it's the kind of transfer function we use. Receptance means forces in Newton input and displacement in output, but we can do the same also for mobility, which is with velocities, or accelerance, which is with accelerations. And this is for a single degree of freedom. This is what we have when we extend the topic to multiple degrees of freedoms. No? So, and as you can see here, what I wanted to stress is that this is by far the most known and most used formulation. No? This is called the rational fraction polynomial, or RFP. And you see that basically the idea is to have a certain polynomial with a certain degree m at the numerator and another polynomial with another order n at the denominator. Now, generally for stability reason, m is much lower than n. This is what you will find in many algorithms, but the key point is that even if it is the most popular formulation, the most used since many decades, this has some technical issues, okay? So the theoretical foundation is solid. The point is that to find the model properties, no? So you have a minimization problem. So you have to fit this formulation on your frequency samples. But minimizing the RFP formulations means that you have unknowns at the numerator and unknowns at the denominator. And because of these latter ones, the problem is nonlinear in its unknowns, and so it becomes non-convex when we try to minimize it. Of course, the classic idea is to linearize it, which just means that you multiply by the denominator on both sides of the equations. But even if you linearize, the problem became ill-conditioned because you see that you have your Laplace variable, so S. You see that it has many different orders. So this becomes quite an issue in technical terms when you try to extract the model parameters from this formulation. So instead, what we do in this case, using this methodology, is to switch from the RFP formulation to the PFE. PFE stands for partial fraction expansion. You see here in its multi-degree of freedom formulation. So here we have capital N modes. And you see here expressed directly in terms of residues and poles of the system. No? So what's the key point we can consider? So again, here the problem is nonlinear in the sense that we don't know the poles and we don't know the residues. No? So again, we have unknowns both to the denominator and the numerator. But we will see that basically the vector fitting iterative schemes works by assuming a set of poles, and then for this known, this assumed set of poles, it derives the residues. Okay, in this way we don't have any unknowns remaining at the below. So then now we will see how it happens in detail. Just another remaining point, of course, generally in practice we are working only on a given frequency range. So we also had a few other terms, you see here D and E, that are just intended to catch the asymptotic behavior, so outside of our curve of fitting, so below our lower threshold and above the upper threshold. One key point that I wanted to stress is that we did not invent the vector fitting, okay? So the vector fitting in reality was something that was already existing and since quite a lot, but in a different field. So it was invented in the field of electrical engineering, and it was intended to be used for the identification of electrical circuits, okay? So when we have not acceleration time series, but voltage time series, no? And so the idea was not intended for mechanical vibrations, so for structural uses, but in the end, we can do it because the core idea is that we have mechanical electrical analogies. No? Mechanical electrical analogies means that you can always define a time-varying mechanical system as an equivalent electrical circuit and vice versa. So basically, you can straightforward translate any algorithm between the two, because you will see that mechanical stiffness can be written in terms of electrical capacitors and resistors. So the implementation is pretty straightforward. The only thing that we need to add is mod shapes, because generally in electrical circuitry they don't care. They have what can be seen as a mod shape, but we don't care. Now, since the next part is about the iterative scheme of the vector fitting, so how it actually works, now I need to introduce some terms just to make what comes next a little more digestible. So let's say that our transfer function is capital HS. So let's consider this the final form, no? So what we want to achieve at the end. So our analytical equivalent of our experimental data. To do so, we will use a counterpart that is lowercase h, which is basically another rational function that will be iterated many steps, no? Every time using trial poles. So at every time we will assume some poles, we will update them. No? The idea is that iteration after iteration we can converge to the actual pole of the systems. No? And then lowercase f is just the experimental value, so the data, the frequency sample we want to fit our analytical function over. And sigma is an auxiliary rational function that we will see in a moment why it came useful. And the other point that I need to explain, just to make some things a little more clear, is that we need to consider P and R as the actual true poles and true residues of our system, while as said, instead, in the next formulation, you will see A and C as the trial poles and in a way the trial residues, so the ones that change and are updated at any iteration. And we will also see why the residues, you see that we have both with and without the tilde above. So at the beginning, I said the vector fitting is an iterative code. So basically, the user needs to define how many modes you want to identify. So what is the model order, we call it. How many iterations, because now we are also developing the variant that can be automatically set the number of iterations, but so far we still set them manually. And of course, the frequency range, so the lower and higher frequency of interest. This depends on your problem at hand. So at the beginning, basically, the algorithm initializes the poles in a totally random manner inside of your frequency range. So at the beginning, you start with a set of poles that are totally random. And then these are iteratively updated, solving solving the following problem. No? So now again, I will try to explain in a few slides, but if I can come back, remember that what we want to achieve is this formulation here. So you see true residues over true poles, okay, capital H. Here, instead, we start with lowercase h, no? And we have, as said, trial poles below and trial residues above, no? What we say is that this function is equal to our frequency samples, so F, so our experimental evidence, times the scaling sigma function. And we define the scaling sigma function as you see there, with the same poles as the trial poles in H, but different residues. So C and C tilde are different quantities. The reason why we do so, we will see in a minute, but this, let me say, it's the point of vector fitting, because the idea of vector fitting, as already hinted before, is not to solve for the poles, but solve for the residues of lowercase h, so to find this C. The reason why we define this scaling function sigma, as we did, is because we can then write the least square problem, as you see here, no? So we say that lowercase h is equal to sigma times f, and so we have the first equation, but we also defined sigma to be in the form reported in the second equation, no? So it means that if we take these two equations and we replace sigma, so from the second inside the first one, after some rewriting, we end up with the formulation you see below in the bottom row. And why it is important? It is important because this is a least square problem of very general kind, no? And we can solve it if we have if we have a very large number of frequency samples. Here it's called the capital NS. The problem is overdeterminated, and we can solve it. But what is important here is that in this problem, different from RFP, you can see that basically, as we said, all the unknowns are in that column vector, so they are only at the numerator, not at the denominator. So it is linear in its unknown. And also, it's not ill-conditioned because you see that the Laplace variable, so S, it's always at the same order, so to the power of -1, so it doesn't change order. So the problem is linear in its unknown and not ill-conditioned. So this is the strength of this methodology with respect to the most common ones, no? And as said, we are not estimating the poles. So we start with some assumed poles. So let's say that for step j equal to 1, we start with a set of poles. From that, basically, what we do is that solving all of these, we obtain, you see, all the residues, so C1 to C capital N, and C tilde 1 to C tilde capital N. There is a tilde missing there, sorry. And once we got these residues, so for given residues and given poles, we can estimate the next iteration poles, so next step, as the zeros of this function. So this is the idea. We at every step, we estimate the residues, which is linear, and then we compute the next set of poles, okay? So this is the idea. And basically, after a certain number of iterations, which is generally pretty low in all the applications we have ever tried, we never needed more than 5 iterations at most, you have that the iterated poles should converge to the actual pole of the system, and also the residues as well. And instead, now it's not reported, but the residues C tilde, so the residues of the scaling function, should instead converge to 0, because sigma instead will converge to 1. And then, in the end, we are back to the basics of system identification. If you have the poles and the residues, you can estimate damping ratios, natural frequencies, and also the mode shapes for all modes of interest. So again, now I don't want to bother you with other details, because I think what is important is the vector fitting scheme, because what we actually used was not the basic formulation, but relatively newer variants, which is called the fast and the relaxed. Relaxed, you see, is just the point of replacing plus 1 in the scaling function with plus d, and not forcing d to be 1, because the idea is that after a few iterations, it should converge to 1, it should become 1, but at the first iterations, leaving it free to take any number, just it's a way to speed up things and remove useless constraints. And also the fast variant, again, basically it doesn't solve explicitly this least square problem here, but since this matrix is extremely big but also extremely sparse, basically it does the QR decomposition of it, which is QR decomposition. Probably most of you knows is just a mathematical tool to get rid of useless entries in big but sparse matrices. But again, these are only technical details that do not change the core idea of the iterative schemes. They are just technical improvements. So, as mentioned, I did my PhD in aerospace. Now I am instead working in the Department of Civil Engineering. So we do system identification on pretty everything. So with Gabriele also, we used and applied this method ranging from buildings to bridges to helicopter main rotor blades and stuff. Here, just to give you something that could be of actual interest for you, this is an application to and F16 ground vibration testing data. The only point is that these are the actual available data set, so you can go on the internet and you can download them. But the authors, that is the Siemens group from Belgium, they only made public 2 output channels out of the dozens and dozens that they used. We actually asked them if they can provide us with the other readings, but it's a military jet, so we're still waiting for a hopefully positive reply. So in any case, here you see that there is one actuator, so it's a single input and only 2 channels, but in any case, this counts as multiple output channels. So this is a classic single input, multi-output application. And yeah, as you see here, basically what we did was trying it on different kind of inputs because basically the authors of this dataset also tried different inputs. At least theoretically, results should be identical, but you know, theory and practice, the practice in theory should be equal to the theory, but in practice it isn't. And you see that these are a result for the sweep sign. So the sweep sign was pretty accurate. So you see those are the in blue the data. So the given experimental FRF input-output. In red is the fitted analytical model using this vector fitting iterative scheme. You see that the results are very consistent. The deviation in blue is relatively, I will consider it good. Then also using multi-sign excitation, results are always, are again, pretty good. So estimations seems reliable, looking at how it fitted both amplitude-wise above and in phase of the FRF below. And instead, and this was expected but always interesting, this instead it's the multi-sign with odd frequencies. So even if the amplitude is comparable to the previous one, we have here more or less 12 Newton root mean square. I mean, since here the frequency grid was smaller because only odd frequencies instead of the full frequency, so the actual amplitude was concentrated in lower frequencies. So overall, the system was more excited. And so basically, at this level of amplitude, with this case of excitation, the structure behave very non-linearly. No, I am not one to tell you that aeronautical structures, whenever the amplitude reach a certain value, start to behave with all kinds of non-linearities due to friction, due to, well, mainly due to friction in these cases. So the point is that since Fourier is linear, whenever you apply a linear operator to a non-linear system, everything became messy, and all these noise-like non-linearity distortions that you see here really provide you with very messy data. Nevertheless, the vector fitting scheme can give you, as you can see, quite reliable estimation of the underlying linear system. And so you can see that the peaks are almost there where they should be. And in reality, that's it, because with these few data applied here, we just benchmarked our results against the values reported in the literature, applied both by the original authors with their own algorithm, which is Polymax. It's a commercial product, and also from other authors that used a more conventional method like the BLA, which is just a best linear approximation. The interesting part about these results, if you want, is that, of course, since the structure was on its wheels, no, it also had some rigid body motions, not exactly at 0 Hertz, but at a lower frequency below 5 Hertz. So these are rigid translation and rigid rotations. They are not flexible modes of the structural component itself. But yeah, generally, the results are very in line with the expected targets and, as said, achieved in a computationally efficient way. And yeah, I wanted to just stress that what's interesting about that, about vibration-based system identification, and I say the structural monitoring is the next step. And also, if you have recordings with and without data, you can compare them and you can obtain and look for anomalies. But what's interesting is the multidisciplinarity, no? Because as I said, in this case, we applied an algorithm that was existing for other purposes in electrical engineering to mechanical vibrations. And even in the main domain of mechanical vibration, as I said, you can apply it to buildings, you can apply it to aerospace. With Gabriele now, we are applying it to the International Space Station recordings, which is very difficult to deal with because of most things. But yeah, you can and you should apply it in many different domains. As long as it vibrates, it can be done. So that's for it. We published, again, pretty a lot on this and related things. I would like to thank Professor Stefano Grivetta-Locia, who is a professor of electrical engineering, who first, let's say, told me when I was still a PhD, why don't you apply this algorithm in your field, since I applied it in mine and it works well. So I should really thank him for introducing me to this idea. And as a last final shameless plug that Gabriele asked me to do. So, but I did accept. So I immediately accepted. So in May 2027, so you have a lot of time, there will be the International Operational Modal Analysis Conference, which is one of our main conference in this field. It will be in Slovenia. It will be held by Professor Janko Slavic, which is a pretty known name in the field. And me and Gabriele will hold a special session dedicated to aeronautical and space applications. So even if you are not in system identification, even if you are just doing vibration stuff, fluidodynamic stuff, whatever, I'm trying to convince you. If you want to join, you are more than welcome to join us in Slovenia. And yeah, with that, I thank you for your attention. If you have any questions.
Thank you, Marco, for your talk. It's time for questions, I believe. Any question on the audience?
Okay, thanks, Marco. Can you hear me? Can you hear me okay? Yes.
Yeah, a little louder. Yeah,
Here now? Okay.
Yeah, now yes, thank you.
Yeah. So I had two questions. One of them regarding your iterative approach. You mentioned that you start with with the poles being totally random values. I was wondering if there's any benefit in maybe choosing values that are more physically significant.
Yeah. Okay. Do you no? Should I respond to this one, or you want to shot the second question as well?
I guess maybe let's do this one first.
Okay. So yeah, well, there is, of course. I mean, so the key. So now to keep things short, because they were already pretty long, I say that the initialization of the poles is totally random. So honestly, it's not totally random. as of now, is they are just supposed to be as much distanced as possible in the range. Consider that these are complex values, so they exist in the real part and imaginary part, and they are set to fill the full frequency range. So they are to fill the full domain, just to have no pole too far from the end result, because because if your initial poles are badly initialized, they may not converge. This happens, of course, this happens. So the idea is that if I don't know anything about my system, let's cover all the frequency range of interest. Since this algorithm is to be applied everywhere, so this is the idea, just full coverage, no? But of course, I mean, that could be a very interesting research approach, so I will take note of that. You can physically, principled, initialize them close by where you expect them to be. That should speed up iterations.
Okay, yeah, thanks. So maybe it would be a bit faster, maybe if you do it.
Yeah.
And I guess the second question about the system, so like you said, this approach is multi-disciplinary and you could apply it to other problems. So I was thinking of like a mechanical system in which you may have time-varying matrices. Like I'm thinking maybe a time-varying mass in a system that your mass is changing over time. I don't know, maybe a rocket problem in which you're losing mass. Do you think this approach could be maybe useful in studying systems like that?
Yes, of course. I mean, you have a lot of great ideas, by the way. I'm gonna steal all of them.
Right, okay.
So
Thank you.
You will be in the acknowledgement. So no, but of course. So whatever can be described as modes, so whatever can be decomposed into modes can be done. So of course here the assumption of stationarity of the system. So I mean, at least in our field, we always work in the assumption of linearity and stationarity of the problem. If you want it to be non-stationary, I think now, never thought about it, but yeah, I think that you can do instead of Fourier transform, you do short time Fourier transform or whatever. So, I mean, you can apply the instant by instant and track natural frequency variations time-wise. It's totally feasible theoretically speaking. Never thought of it. So yeah.
Okay, great. Thanks, Marco. That was all mine.
Is there any other question, or I go with one question and we finish then? Can you elaborate a bit more on the application of this methodology that you intend to do together with Gabriele to this ESA? I don't remember what you mentioned at the end.
The International Space Station.
To capture which type of vibration. So what is the aim of the activity, if you can elaborate a bit more?
Yeah, definitely. So the aim is because it's cool. No? I mean, I honestly, because I mean, you guys are aerospace engineering, no? But on the aeronautical side, there are data sets. No, I mean, even me, I did my PhD, so I have a data set of a wing. Gabriele has one of his own wing. So it's more difficult to, or at least I did not find many space vibration data sets. And what I think is that, well, of course, these ground vibration tests are commonly done in satellites, no? Because of course you want to know the natural frequencies of your satellite, CubeSat or whatever, before launching it in space, because maybe it goes in resonance with exciting dynamics forces during launch and propulsion and stuff. So these are generally done. I'm not the one to tell you, you already know that. And it's also interesting because when they are up in the space, Well, first of all, they are floating, so there are all the rigid body motion components no, at 0 hertz. And also what we found with some master students working on this dataset of the International Space Station is that since it's a very, very complex structure, there are a lot of modes, like you can find hundreds of vibrational modes, many local ones of small branches, many local modes. And the natural frequencies are extremely low. So you have a lot of modes that are below 1 hertz. So again, good luck discerning a rigid body motion to a low frequency flexural mode. And also the boundary conditions, no? Because again, one thing that is very well known in this field is that stiffness matrix is not only changing due to damage, but it changes also because of environmental conditions. No? So the stiffness, of course, is very, very much influenced by temperature. And yeah, so the fact that the International Space Station rotates around the Earth, so it has no air, so so there is not exchange of heat because of air, but every 30 minutes or something pass through the shade of the Earth to sunlight. So there are these quite relatively rapid change of temperatures. They do influence, so you have a lot of weird fluctuations in the identified model parameters. So it's a pretty unique and interesting application.
If there are no more questions, I think we can. Oh, okay, Gabriele. Then. Very last question.
Yeah, Gabriele, we want to go lunch.
Just a comment on that. It's just a comment on the space station. Well, the idea is the monitoring itself. So as Marco said, it's a complex system. You have very low frequencies and such. So the real issue there is also you want to track events. For example, a docking of a spacecraft to the International Space Station, that will change your natural frequencies. But then what happens when it dechatters, right? It goes back to Earth. And when it comes back to Earth, then the frequencies should go to somewhat what they were before, right? And if they don't, then you're monitoring the structure and you can find potential damage sources or any other sources of difference from the original structure. So that's the main idea. And that's also what Marco was saying throughout, is that system identification then feeds into the monitoring.
Okay. Thanks very much. Let's thank Marco again. And
Thanks for